If you've ever told a joke, you understand how important timing is. That little bit of time between the setup and when your punchline lands has to be perfect. It's the same way with digital logic. The information has to give enough time for the setup to happen, or our audience won't get it. It's one thing that separates good digital design from the average, a consideration of timing. First, let's clarify what I mean by digital logic, because you're probably thinking about computers. Your computer, maybe your phone. That's not wrong, but a computer is just one specific type of digital circuit, like your Honda is one type of vehicle. Programmers don't need to worry about timing. When you write a variable to memory, you trust that variable will make it to memory. You trust the digital designer did his job properly. Very briefly and in plain English, a digital circuit is a circuit that manipulates data. To put it pedantically, a digital circuit is a circuit that physically implements a digital system, which is a system that performs operations on information encoded into discrete states. There's just a lot of context packed into the casual definition. Implicit in our definition is the system's ability to store data, to hold it in time, which is technically optional but practically essential, which I'll get to. I've said in the past that a computer is a machine that manipulates memory, and that is an extension of this broader principle of digital circuits extended to that one specific manifestation. Practically, the simplest unit of a digital design is some manipulation of data, followed by the storing of the result. The former is called the combinational logic, the latter is the register or memory element. In a sense, digital logic is just one big chain or tree of these units. This method of explicating the design is called register transfer logic, or RTL. RTL is just one paradigm by which a designer can express a system. For the purpose of this discussion, it's all we need to know. But a good designer should be considering all of these paradigms when implementing or assessing a design. When we're constructing our system, we like to think of our signals and logic as instantaneous. More accurately, we don't like thinking about how they're not instantaneous at all. Unfortunately, these building blocks are physical things in the real world. And physical things take time to change. Signals take time to propagate through a wire. Transistors take time to change state, which means logic gates take time to propagate inputs to outputs, and memory elements take time to remember things. So our combinational logic is a network of logic gates, registers are memory elements, and they're all connected by wires. So a signal that starts here takes some time to get to the combinational logic, some time to pass through the combinational logic, some time to get to the register, and some time for that register to accept the new data. We can start making sense of this by ignoring wire propagation. The switching times on the logic elements will be your limiting factor by far, unless you're working on a borderline fictional transistor that can operate at 10 gigahertz, or you're working on a very fast design spread across a very large chip. Which does happen, but most of us have to build practical things. The combinational logic will take some amount of time to propagate. For the most part, you can't do much about that. Performing this data manipulation is the whole point of your design. At some point, you can't make it smaller. Which leaves the registers. This is one thing we can control, so we need to understand them, hold them, sympathize with them, try not to break them. A register, generally some kind of flop, is a special combination of transistors that can persistently hold one state. Unlike a logic gate, which jumps to a new hyperfixation whenever shown something new, a flop only changes when it's told to. Zooming out, we casually call this clocking data into the register. If you hear someone say, yeah, that reg is clocked off 6 o'clock, it means when a special signal called the system clock changes state, the register grabs whatever is at the input and holds it until the next state change. So we have our first timing concept and design consideration, the clock. We generally use a clock edge to trigger a register update, usually the pause edge, occasionally the neg edge, sometimes both. Our data has to be available at the register input before that clock hits. That lead time actually has physical importance. Remember, registers are just devices built from transistors. If you look inside a register, the first stage is actually constantly following the input signal, just with a slight lag. Remember, transistors take time to change state. When the clock strikes midnight, the state of that input transistor is used, not the voltage on the wire leading into it. The other transistors won't wait for the input transistor to finish changing. They'll barge in. If you're not dressed for one specific occasion, everyone will be confused, and the whole register gets into an ambiguous or metastable state, which is bad. On the flip side, if you arrive dressed properly, you generally need to stay dressed properly. In the same way you don't put on pajamas until after the fancy dinner is over, the voltage going into the register has to stay constant until after the data has been stored. So the data needs to give the register enough time before the clock transition for the register to set itself up, and the data cannot change for some time after the clock event, so the register can take and hold that data. Respectively, these are the register's setup and hold times. Together, these give us constraints on how to construct our RTL. Signals need to pass through the combinational logic in less time than the clock period minus the setup time. And the hold time, but we'll get to that in a sec. But what can we really do? We can't change how the register behaves, and we're assuming the combinational logic is as lean as it can be. The one thing we can control is how the combinational logic gets divided into chunks. By dividing the combinational logic and inserting registers in the gaps, we can turn a single RTL unit into a chain. Signals now only need to pass through a small chunk before the clock event. However, each combinational block is now fed by a register, which has two significant consequences. First, a register's data needs to be constant for a short time after the clock event. That eats into the available time our signal has to propagate through the combinational chunk. Second, each stage can only ever be as fast as one clock period. This introduces a major trade-off. As you try to run a design faster and faster, the amount of leeway or slack that you have gets smaller and smaller until it becomes negative, in which case your signal won't reach the register at the other end. You can tweak the design and add stages to the pipeline, but that can massively increase the latency. This trade-off is a major design consideration in the realm of the RTL paradigm. And the answer isn't always make the pipeline stages as large as is allowable by the clock. Take this SHA-256 hasher FPGA design I've been working on. I took the pipeline on this to a ridiculous extreme, adding a stage for even negligible operations. It's borderline wasteful in terms of resources and has a massive amount of clock latency. However, it processes a new hash on every single clock. Part of my reasoning was from a desire to crank that clock, sure, but part of it also comes from the incompatible nature of the algorithm.